Okay, in this video we take a look at the dynamics of a rolling object. First of all, on a horizontal surface. Okay, besides F equals ma, we're going to apply the following expression. Net torque equals I times alpha. Okay, this expression does apply to an object undergoing a rotation and a translation, all with respect to an inertial reference frame, provided that the rotation is about the center of mass. So specifically on the right-hand side of the expression, the rotational inertia I is the rotational inertia about an axis passing through the center of mass, like so. Okay, so we have, for example, my tennis ball. It rolls horizontally across the desk to the right-hand side. It slows down as it does. So let's apply F equals ma to the situation and tau equals I times alpha as well. Okay, now I'm going to go ahead and do some erasing here. Let's draw out our situation. We have the following. Okay, so first of all, right here is our surface, and then right here is our object, like so. Right here is the center of mass, and then once again, the axis of rotation passes through the center of mass. Okay, the object is rolling in this direction. However, it's slowing down as it does. Therefore, the acceleration vector, of course, applies to the left-hand side. Okay, and then let's just draw out a force diagram, that is the forces exerted upon the object, as we always do when examining the dynamics of a situation. We have the following. First of all, of course, is the object's weight. The object's weight mathematically behaves as if it's applied to the center of mass. And then we have static friction between the ball and the table below that is ultimately causing the rotation. It's also causing the object to slow down. Think of it this way. In which direction relative to the desk does the ball tend to slip? Like so, to the right-hand side. So preventing it from slipping to the right-hand side has to be the force of static friction acting on the ball to the left-hand side, like so. So right here at the point of contact, right here then is the force of static friction. That gives us the acceleration to the left-hand side. And then of course we have the normal force, so the ball presses down on the table, and then therefore the table presses back up. We have the normal force vector. I'll draw this in a different color, like so. I'll draw it in green, like this. And now let's just go ahead and add up the forces first. Okay, first of all, vertically, everything cancels out like so. And then horizontally, we have the force of static friction giving us the acceleration to the left-hand side. So we'll treat the force of static friction as a positive number as we always do. That is, it points in the same direction as the acceleration A, so then therefore we think of it as positive. So the force of static friction equals ma. Okay, now let's take a look at the torques that are exerted upon the ball due to the forces as the ball, for example, rotates and rolls to the right-hand side. Okay, so first of all, we have the force of gravity, mg. Immediately, what can we say about the torque due to gravity? It's equal to 0. And the reason for that is because the moment arm, r, is equal to 0. Recall that the moment arm goes from the axis of rotation, that's the center of mass, to the point where the force is applied, while the force of gravity mathematically behaves as if it's applied at the center of mass. So then therefore there is no moment arm in r cross f, therefore the torque due to gravity is equal to 0. So torque due to mg equals 0, no moment arm. Okay, now let's take a look at the torque due to the normal force. So the normal force is applied right here, pointing straight upwards like so, and then we have our moment arm going from the axis of rotation, the center of mass, to that point. There's a 180-degree angle between those two vectors. So here off to the side like so. This right here is the radius of the ball. Right here is the normal force like so. And then this angle right here is typically referred to as phi in this situation, is equal to 180 degrees. Now the sine of 180 degrees is equal to 0. Therefore, there is no torque due to the normal force, referred to as tau sub n. And then we've got the force of static friction. Watch this. We have, first of all, our moment arm r, like so, and then the force of static friction pointing to the left-hand side. So here's r, and here's F sub s, and there's a 90-degree angle between the two vectors. Sine of 90 degrees is equal to +1, therefore the magnitude of the torque is nothing more than R times Fs. However, watch this. R cross F is into the board. Notice the direction that my fingers are curling. They're curling in this direction. In other words, this torque wants to cause the rotation of the ball to increase. It's opposite of what we're referring to as the direction of the acceleration being the positive direction. This is a negative torque for this reason. So now the torque points into the board like so. Once again, R cross F, but take a look at the direction that my fingers are curling. They're curling to the right. So then therefore the torque vector is trying to increase the rotation of the ball. It's trying to increase its rolling motion as it rolls across the desk. Therefore, we have to think of it as a negative number because it's opposite of the acceleration, which we're thinking of as positive. So then therefore, I end up with this torque like so, equal to I times alpha. Alpha, of course, is equal to the acceleration A divided by the radius R. But there's something wrong here. How could I have this negative sign present when we know that the right-hand side of the expression is in fact a positive number? So then therefore there is something wrong here. This is a positive number. This can't be a negative number for that reason. So then therefore, how do we resolve this apparent contradiction? There's something wrong here, as I've said. It has to do with the normal force. I was implying, or I was assuming rather, that the normal force is applied right here at a point directly below the center of mass, and it then points upwards like so. If you assume that, you are assuming that the tennis ball is a perfectly rigid object. There's actually no such thing. All objects, in fact, sag a little bit under their own weight. So because all objects sag under their own weight, this then means that the normal force is not applied directly below the center of mass. It's actually applied a little bit ahead of the center of mass as the ball rolls in this direction. It's a little bit difficult to understand that with a semi-rigid object such as this tennis ball, but it's actually quite obvious here in the case of this little foot bag or this little hacky sack. So for example, watch what happens to this hacky sack, which sags a lot under its own weight, for example, as I roll it in this direction. Like so. Notice that it slows down almost immediately, and the reason for that is because the normal force does not point straight up passing through the center of mass. It points straight up, but slightly ahead of the center of mass. This is due to the rolling motion of the inertia of the object itself and the fact that the object is not perfectly rigid. It sags under its own weight. If there was such a thing as a perfectly rigid object, it would actually violate conservation of energy because of this situation. For a perfectly rigid object, the torque that's exerted upon it due to static friction would ultimately cause the ball to speed up. Where did the energy necessary to do that come from? It would violate conservation of energy. So for this reason, there's no such thing as a perfectly rigid object. The object does sag a little bit under its own weight. This then changes our force diagram slightly and adjusts the expressions slightly. So here's then what really happens. Now, much is the same as what I described before, so I am leaving a few things here on the board for that reason. Okay, so here's our ball again, like so. Okay, it sags a little bit under its own weight, as I said. Right there is the center of mass. Once again, the axis of rotation passes through the center of mass. Here's the rolling motion, like this. Okay, and then we have the following forces. So we still have mg, like so, applied at the center of mass. There's no torque due to gravity, once again, because there's no moment arm. There's no R in R cross F. All of that is the same. Okay, right down here, we once again have the force of static friction. That then gives us our acceleration to the left-hand side. So then therefore, when we add the forces here horizontally, we still have F sub S is equal to ma. Nothing changes. Once again, we still think of this as the positive direction. And now we've got the normal force vector. The normal force vector is slightly ahead of the center of mass. Once again, that's due to the rolling motion and the ball's inertia, like so. I'm probably exaggerating its position a little bit, but the normal force is slightly ahead of the center of mass because once again, there's no such thing as a rigid object. It's sagging a little bit under its own weight. This then means that right here from the axis of rotation to this point is a moment arm where the angle then between that moment arm and the normal force vector is not quite 180 degrees. Instead, it looks like this. So right here is R, right here is the normal force, right here is the angle phi. It's less than 180 degrees. So then therefore there is a torque due to the normal force. Let's check its direction. So if you do R cross F like so, you end up with a torque vector that's out of the board. That torque vector out of the board, that's what's trying to slow down the rotation of the ball like so. Therefore, we have to think of that as a positive torque because ultimately the angular acceleration gives us a tangential acceleration that's in the same direction as A, which we're thinking of as positive. So then therefore this torque here, we just refer to it as tau sub n. It is in fact a positive number, R cross F coming out of the board like so. So then therefore we add this to the negative torque associated with static friction. This then gives us our net torque equation in the following way. Tau sub n minus RFS is equal to I times alpha. Once again, alpha is equal to A over R for a rolling object. Like so. Okay, now the acceleration of a rolling object typically is very small. Like so, it takes a while for the rolling object, of course, to slow down and stop, unlike an object due to friction, for example, which slows down very quickly when it's translating like so. This tennis ball, however, will probably roll for a good 30 seconds, ultimately off the edge of the desk if I let go of it. So then therefore, because the acceleration of a rolling object is typically very small in a horizontal situation, this then means that there's not much difference between these two numbers. In other words, it's just a slight positive number where this numerically is slightly bigger than this number here, ultimately causing the ball to slow down. Now, in order to do an actual problem involving numbers and so on and so forth, we would actually need to know what this angle is right here, for example, between the normal force and the moment arm to actually do a numerical example. You will not encounter such a situation as a problem on the AP Physics exam or in homework or anything like that, but you may encounter this situation on the AP exam qualitatively, where they may ask you, for example, to explain why an object rolling horizontally like so does in fact slow down. This is the reason why.